Mercury. Today is Wednesday, and in many Latin languages, especially Italian, Wednesday is Mercoledì, is the day of Mercurio, the god Mercury. So it's a perfect day for talking about this planet. And your teachers will be myself. I'm a researcher at INA-FIEPS in Rome. Then later you will hear a lesson by Dr. Christian Carli, who is as well a researcher here at INA-FIEPS in Rome. And then for our final frontal lessons in the morning, Francesca Zambon will speak about Mercury spectral data. So just a quick overview of our today's schedule. And we will start soon with my lesson on Mercury surface morphology. Then Dr. Carli will speak about the Mercury surface composition. We will have a coffee break at 10:30. And then we will continue with the Mercury spectral analysis by Francesca Zambon. And then we will review Mercury-based data and mapping for everyone. As Erika was saying, at 11:50, more or less, we will do the Zoom link change to do the Mercury practical. So for all the participants, don't forget to follow the come back, reconvene to this plenary room at 6 p.m. Central European time to follow the invited talk by Professor Crane. Okay, let's get started with the Mercury surface morphology. This is a quick overview to introduce you to this planet. This planet was observed already in the since a long time ago, but starting from the 19th century, some astronomers started producing maps about what they saw through their telescope. And the most famous one were the one by Virginio Schiaparelli and Percival Lowell, who did also some observations of Mars in the same period. So they were in some way, let's say, in some way they looked at Mercury as they looked at Mars. And as you can see from all these scars that looked like canals on Mars. But Eugene Antoniadi in 1934 did probably the best map from a telescope that we have so far. In fact, these names that Antoniadi gave to the albedo region of Mercury are still in use today in the official nomenclature of Mercury. Then the space mission started to visit the planet, especially in the 70s, when the Mariner 10 mission did the 3 flybys of the planet and covering 40% of the planet's surface during the flybys. So this was what, so this was what we knew about Mercury in the 70s. So 30 years later, the NASA Messenger mission entered its orbit about the planet and finally covering the whole surface at 100%. So we finally came to know the entire planet thanks to this mission. Now the Bepi-Colombo mission, a joint mission of the European Space Agency and the Japanese Space Agency, is making its journey to Mercury. It just completed the first flyby in October, and Bepi Colombo will arrive at Mercury in 2025, December 2025, when it will start its orbit about the planet with two spacecraft, the MPO spacecraft and the MMO spacecraft, also called MEO, that will study the planet with interdisciplinary studies and 16 different instruments. So its name, Bepi Colombo, comes from the scientist Giuseppe Colombo, an Italian scientist that permitted in the 70s to the NASA mission Mariner 10 mission to do 3 flybacks instead of 1. So Bepi Colombo is the one who understood the dynamics of planet Mercury, and thanks to his calculations, now we can go to Mercury and enter its orbit today. So Mercury is the first of the I hope you don't see my Zoom panel here because it's in between. I was like, okay, great. Okay, so Mercury is the first of the planets of our solar system and the first of the terrestrial planets, and is also the smallest one. It is an extreme planet. And yeah, its diameter is slightly larger than that of the moon. It's 4,880 kilometers. And it is also the densest planet. Of course, there is some exception with Earth if we look at the bulk densities, but of course, as you could expect from the distribution of planets around the solar system, Mercury is absolutely the densest planet. And okay, I could tell you that this is Mercury, but I know I won't fool you because yesterday you did the moon lesson. So you will recognize this as the far side of the moon. And this on the right side is actually Mercury. So from these two pictures, you can see how these two planetary bodies are very similar to each other. They are very largely deeply cratered around their surface, with a slight difference on albedo. In fact, Mercury is slightly darker than the far side of the moon. But if we look at the near side of the moon, then probably the moon here has a lower albedo than Mercury, while Mercury has more rayed craters, so it has a higher albedo when looking at rayed craters. Mercury has no regions such as those of the moon Maria. It's all pretty similar, and let's have a look at its surface. The surface is densely cratered. We prefer the word densely cratered to heavily cratered because it has less craters than the moon. It's not as heavily cratered as the moon is, and we will see why. So as the moon, Mercury also has a lot of craters with rays that embrace entire hemispheres. So the main features when looking at Mercury with monochrome pictures, the most important ones are probably the Kuiper crater here that defines the youngest period on Mercury, and the Tolstoy crater on the other side that defines the oldest period of Mercury. So Kuiperian and Tolstoyan are in contrast as in the time scale of Mercury. We also see, by looking at its topography, we can see that there is a large planitia in the northern region of Mercury. This is very, very large and extended. These are very extended smooth plains that cover the entire northern pole of Mercury. And while for the heights, you can see that the heights of Mercury span from 4.5 kilometers to minus 5.38 kilometers here. And there is not much variation, and it's pretty monotonous. However, thanks to the topography, it was noticed that Mercury has large scale undulations in the topography. When looking at Mercury in false colors, it's clear that the northern planitia that we saw before is also very yellow in false color, and this region is called Borealis planitia. On the other hemisphere, we see another plane, round plane here, which is a giant impact, and in the solar system is one of the youngest large impacts, and it is called Calores Basin. This is Calores planitia here. And from false color, it is evident also that Mercury has a lot of blue planes that often correspond to densely cratered regions, and these are called low reflectance material. Okay, so why it is so important to study surfaces of worlds like Mercury? Just compare them in the time scale of Mercury to that of the Earth. What do we know about these two planets? Well, the surface evidence of Mercury is complementary to that of the Earth. In fact, on the Earth, we know pretty well the outcrops of the Phanerozoic eon, some of the Proterozoic eon, while the Archean outcrops are very, very rare. So we know we have little evidence of the origin of our planet. While on Mercury, there is strong evidence for its origin and its oldest terrains, and less evidence for recent resurfacing and processes for its surface. So both planets were characterized by these the late heavy bombardment periods that maybe you knew something about yesterday. And so Mercury preserves the scars of this period as well as the Moon does. So this is a fossil remnant of the origin of our solar system, and it's very, very important to compare it to our planet and the other planets to understand the evolution of our solar system. So if we look at Mercury in false colors, it's evident that there is much variation. And since there is no atmosphere, there is no other kind of processes that cover the surface, these images are just like a geological map, because the surface is like naked and shows all its units with these false colors. So it is pretty diverse, but we have to say that these are all volcanic units. So the surface of Mercury is covered in lava flows that happened in several periods of its history and overlapped one over the other. So differently from the Moon highlands that we have looked before, they looked very similar to Mercury, but differently from the Moon highlands, Mercury has a secondary resurfaced crust by volcanic events, while the Moon highlands actually are the evidence for the primary crust. So this is a strong difference between the two planetary bodies. And the low reflectance terrains are thought to be the evidence for the primary crust that is often exhumed by impact craters. So this is a scheme on what could have formed Mercury plains at its surface. But its surface is characterized by widespread scarps. You may already know wrinkle ridges by looking at the moon, but Mercury actually has a lot of scarps, such as this one, which are much more prominent than the moon scarps. These are called lobate scarps, and there are thousands of them on Mercury. This is one of the most prominent ones. And so lobate scarps of Mercury, what they are actually the surface expression of faults. In fact, all these hills and scarps are the expression of thrust faults, reverse faults that cut the surface, and let's say, as happens on Earth, the hanging wall slides over the footwall. You will hear more about Mercury's tectonics this evening, thanks to Professor Crane's invited talk. So why does Mercury has all these scarps? We have to do a step back to its formation. So, you know, all the planets formed in a process known as accretion, and they produce clusters of planetesimal up to producing protoplanets. And in this process, a lot of heat is generated. So the planets, the protoplanets, are very, very hot bodies that produce a lot of energy because of accretion. But at a certain point, the body starts to cool down and differentiate into a core, mantle, and crust. And it continues to cool down in time. So this cooling process is likely the cause of all the scarps that we observe on Mercury. Especially Mercury has a very large core. As you can see from this image, the core of Mercury has a 2,000 kilometer radius. That, if you compare it with that of the Earth, is very, very large. It occupies almost 80% of Mercury volume. And so you can imagine that a planet with a core like this, while it cools down, the effect on the outer shells is very strong. And that's why it's very easy to see on Mercury so many contractional features. So this is the process from the hot planet in the origin that cools down, and then volcanic plains forms on its crust, and then the cooling process and global contraction in Mercury causes the formation of these scarps. And this is just a curiosity. Also in the 19th century, in 1829, Léon Célie de Beaumont stated that Earth is in a contractional state. They didn't know the presence of plate tectonics yet, so they explained the presence of mountains on Earth with a process similar to that is actually happening on Mercury. Now we know that plate tectonics is a unique process on Earth, while on Mercury, this process that Beaumont spoke about is actually happening. And there are thousands of scarps, so that we estimate 5 to 7 kilometers radius change since when Mercury was hot and up to today. So, but these are not the only important features that are present in on the planet. We spoke about effusive volcanism. Unfortunately, there is no evidence of volcanic edifices, just like we see on Mars, for example, or some on the moon also. There is nothing like that on Mercury, but we can see a lot of explosive features. In fact, Mercury has several vents, which are the surface expression of several pits that are the surface expression of volcanic vents, explosive vents. And when looked in false colors, these show a bright yellow halo around them. And the halo of the vent is usually much, much larger than the vent itself, which is here in the middle. And since we have many vents and many lobate scarps, in some cases, these are actually aligned with the lobate scarps and folds. For example, here you see a scheme of this group, this system of lobate scarps, and exactly at the northern end of the system and in the middle of the system, you find three vents. This on the right is another example of lobate scarp, discovery lupus in the southern hemisphere of Mercury, and in front of it you have a series of vents. So the correlation between vents and folds is sometimes very similar to the correlation that we have on Earth between the, let's say, contractional margins and volcanism. However, in here, the geodynamic context is pretty different. So to understand other Mercury features, we have to take into considerations that Mercury experiences the largest temperature variations on its surface. And this happens because of its high eccentricity, a vertical axis, and a spin orbit resonance with the Sun of 3 to 2. So every 3 rotations of the planet around its axis, it completes 2 revolutions around the Sun. So these combinations of factors causes Mercury to have cold poles to the north and the south pole that never see, let's say, never see the direct light of the Sun, and the hot poles near equator regions where we experience the maximum temperature. So the maximum temperature variation around Mercury's surface is from 450 degrees Celsius up to minus 180 degrees Celsius. So this surely, let's say, causes something on the surface, no? In fact, in the poles of Mercury, it has been discovered, firstly theorized in the 90s, and then discovered by Messenger, that there are some permanently shadowed regions that also may host water ice, because these permanently shadowed regions permit the ice to stay there and permit the water ice to stay there. And on the contrary, in the hot poles and in the latitudes, at the low latitudes next to the hot poles, it's very easy to see these features here that we will see in the next slide. So these features are called hollows. Hollows are small holes of about 100 meters. They often cluster together. They are often found within impact craters. But as you can see from this map, there are no hollow fields in the northern regions of Mercury, in the cold poles of Mercury. They are all scattered near the hot poles regions. but their correlation is strong, actually stronger with the low reflectance material. In fact, you can see there is a high concentration of hollows in the regions where we have blue planes, with respect to those regions where we have yellow planes. So the correlation is stronger with the composition of the crust, but there is also a contribution from the surface temperature. So hollows seem to be informed by a sublimation process. However, these are still a mysterious feature. So they still need to be studied in detail by the future mission, Bepi Colombo mission. So latest news from the Bepi Colombo mission are that Bepi Colombo got the first pictures of Mercury, and these pictures show the planet. This is pretty unchanged since the messenger last saw it, but it was an incredible feeling to see these pictures after 7 years after messenger. So next flyby will be in June, 22 June, and you're all welcome to follow the news, to follow next pictures of Mercury. So this presentation of Mercury is, I'm afraid I was a bit too fast. This is over, but I invite you to make questions and ask me more about Mercury surface features, because I just made you an introduction, and if you wish to have more details on the surface features, I'd be happy to answer your questions.
Thank you very much, Valentina. Yes, indeed, that was very fast. So I guess we will leave 10 minutes maybe for a coffee, since we have, or maybe if you have questions, we can take questions. Instead of dropping in the chat as usual, you can live questions this time. I think we have one. Matthew is asking, how do they decide where zero elevation is on Mercury?
Okay, great. On Mercury, as on any other planet, there are, okay, let me take back the elevation slide. Okay. On Mercury, as on any other planet, the elevation is calculated on, let's say, reference sphere. So geophysical instruments and geophysical studies can assess the mean diameter of the planet. So by the mean diameter of the planet, we take a reference sphere, and this is called the datum in geographic information systems. And so the mean radius of the planet is considered to be zero height, and everything else is plus or minus with respect to the main reference sphere. So we have no sea level. Okay, you have to consider that the sea level is the mean radius of this body. Which is, in the case of Mercury, 2,440 kilometers.
We have a lot of other questions that are up. What about the, what about Celtic terrain on Caloris antipode?
Okay, great questions. It's actually one of the Mercury instructors that will follow Mercury practical this evening is actually studying that area of Mercury. So let me take the right slide to catch the antipode. So the antipode to Mercury, to the Caloris basin, which is here, is around this area here, which is the discovery quadrangle, called the discovery quadrangle. I don't have any picture here, but we can explore together Mercury quick map, and I will share another screen now. Okay. Hope you can see in my my screen. Can you see the Mercury quick map?
Yes.
Here?
Yeah.
Okay. So later in the morning, I will explain you how to explore this quick map. This is the messenger quick map, a place where you explore, where you can explore all messenger data. So since I got a question about the rough terrains, chaotic terrains on the antipode of Caloris planitia, this is Caloris planitia. So we have to go to discovery quadrangle, which is around here. Okay, great. This is discovery lupus, a famous lobate scarps, one of the first that Mariner 10 pictured. And the chaotic terrains are here. We can change the base map. Oh, here they are. Here they are. So they are pretty nice because you can see that the craters, also young basins like this one, have very strange rings. They are show sets of fractures. Sometimes they interact with each other at right angles. And these are called chaotic terrains. And it seems that they were caused by some post-impact process due to the large impact of the Caloris basin. So a sort of seismic effect of the impact to the antipode of the impact. Actually, these terrains are still under study, but you see the texture is very particular because around the rims you can see many fractures, and this is different from any other rim. For example, this is a normal rim of a complex crater, while these craters here have a fractured and very rough texture. And yeah, I bet if you are following our Mercury practical, Alistair Blance, who is working on this quadrangle, on the mapping of this quadrangle, can give you more information on these terrains here. Okay, here we have another place here, very interesting with chaotic texture. Yeah. Okay, another question. Yeah.
They're quite different from the Martian chaotic terrains, though. This is the first time that I see chaotic terrains on Mercury.
Yeah.
They're a bit different.
There are some people that are not convinced they are the effect of the Caloris basin. So there is also a lot of studies going on in these terrains.
That's nice. So guys, if you're inspired, maybe
yeah,
future problem solvers. So the next question is, what is the main difference between wrinkle ridges and lobated scarps?
Okay, great. Yes, that's from a morphological point of view. Since we are on the quick map, I will use the quick map to help you. So from a morphological point of view, wrinkle ridges are smaller scarps, and they often form ridge like this one here. Sorry. Okay. They often form ridges like this one here, and you can see a scarp over here and another scarp on the other side. They are not so high as lobate scarps. So basically, a lobate scarps is a very large wrinkle ridge that has finally a preferential sense of propagation. But from a structural point of view, this is a lobate scarp, Victoria lupus. From a structural point of view, they are pretty similar. I mean, they are both the surface expression of thrust faults, so reverse faults, contractional features. But in the case of low base curves, the thrust faults are break the surface and create prominent scarps, while in the case of wrinkle ridges, thrust faults are often blind and do not break the surface. They stop just beneath the surface, and what we see on the surface is just a fold on top of the thrust. So this is the difference between the two features. Mainly a morphological difference, not a structural difference.
Okay, we have a question now that maybe is overlapping a little bit with the next speaker. The question is, are pits associated with a certain spectral type, such as volatile rich compositions?
So I can only, let's say, introduce the answer to this question, but Christian and Francesca will go deep into this, into this matter. And so let's open the enhanced color base map. So in general, there is strong evidence for volatiles on Mercury. There is strong evidence for volatiles. And the presence of this faculae, which is the descriptor term of these yellow regions and bright regions, from the spectra, it is clear that there is a different composition from the surrounding terrains. That I don't think we have the precise composition, but the very existence of these vents already tells us about the presence of volatiles beneath Mercury's crust. Another evidence are hollows, for example. And it's not rare that we see hollows and faculae together. Let me search for a place where, okay, here, I have to go back here. Canova, here. This little crater here, Canova, shows a lot of hollows, a hollow field, an important hollow field here. Then you can see hollows scattered in bright blue color, but in between them we have a orange to yellow facula. So these two features are often found together, and they are both evidence for the presence of volatiles. But for the composition, I invite you to follow the next two talks that we go deeper into this matter.
Thank you, Valentina. Next question. Is Mercury's larger core more attributed to the metal composition it contains, or is it rather its closeness to the sun?
Okay, let me share the screen again. Neither of the two. It seems that some theories show that Mercury probably is formed as a larger planet. Can you see the slides?
Yep.
Okay, so latest theories think that Mercury formed as a larger planet, as larger as the Earth, maybe. And as it often happens in that time, during early solar system formation, giant impact happened, such as that of the planet Theia with the Earth that formed the Moon. So something similar probably happened with Mercury, stripping off all the outer shells. So the Mercury core is so large probably because Mercury was larger once in early solar system formation. This is the main theory that is being considered today.
Thank you. Could you underline the main formational structural differences between highlands and planitia?
Okay, we don't structural formation. When we say structural formation is something related to tectonics, while on Mercury, the plains are not a product of tectonics, but on, let's say, several volcanic events that formed them. We don't usually use the term highlands on Mercury. This is more typical of the moon. We usually call them plains, them all, but the main difference is a morphological difference. The northern plains are very smooth, much less cratered, so they are younger. So this is, we can say that this is the youngest volcanic events that cover the surface of Mercury. While for those that might look like highlands, let me turn on the DTM. Okay, let me see where the DTM is. Here. Okay.
We're still watching the slide.
Ah, sorry. I was speaking on the. Okay. Okay. I will change again my screen. Here I am. Okay. So what you could call the highlands, so high terrains, are indeed often characterized by rougher terrains, but not all of them. So we can't say that the Mercury highlands are a different unit from Mercury lowlands. Rather, we have smooth plains and rough plains that we call intercrater plains. And later this morning, we will see there is also a formation that can be called intermediate smooth plains. But basically, we have smooth plains and intercrater plains. And they may be low or high, so we don't distinguish between highlands and lowlands. In both cases, they have a volcanic origin. They are both terrains are volcanic plains, volcanic flows that cover the surface, a secondary crust caused by volcanic effusive events. We don't have volcanic edifices around Mercury because probably these volcanism happened through fractures and let's say rills that are scattered below the surface. So there is not actually there is no structural difference. It's not tectonics creating high terrains and low terrains. It's just volcanic events and impacts. Hope I was clear. Yeah.
Next question. There are a lot of questions. This is awesome.
Great. That's why I was free.
Yeah. That was a good idea indeed. You mentioned that Mercury is entirely resurfaced and it's all secondary crust. Why this difference? How large are any areas of primitive primordial crust exposure? Are they solely exposed by exhumation or are there areas of uplift from below? How small of a fraction of the surface do these areas represent?
Okay, that's a good question. Latest theories say that actually what we see is mostly secondary crust, entirely resurfaced by volcanic events. Okay, but there are some studies that say that these dark blue plains might hold the composition of a primary crust, which is actually below these volcanic plains. But these terrains might hold the signature of a primary crust. certainly all these craters that have blue plains and blue materials around them certainly exhumed something from below, which is similar to the primary crust. Some researchers say that this primary crust is made of graphite, and Christian Carli in the later talk will talk more about this. But since we are not sure whether this is primary crust and what is its composition, I cannot tell you which is the percentage of primary crust with respect to secondary crust. But Christian will tell us more about this matter in the next talk.
Then we have a question from Vidya Ganesh. He says, I remember reading some abstracts about identification of slope-like features on some crater slopes in the mid-latitude regions of Mercury that look very similar to spur and gully morphologies on Earth and Mars. Do we know what might be a causal factor for these features? And by extension, how recent could these features have been formed?
Okay, I'll take back the question because it's pretty long. So,
so he's asking why and what's the extension of slope-like features on Mercury that resemble gullies on Mars and Earth?
Yeah. So yes, it has been observed that there are some features similar to gullies on Mercury. Unfortunately, we don't have many frames, high-resolution frames from the messenger mission that permit us to study these gullies in details. However, yes, I think I read the abstract. There is a database of places where we could study something similar to gullies on Mercury, but certainly we will need higher detail from the Bepi-Colombo mission and from the pictures that Bepi-Colombo will capture about Mercury. Unfortunately, Mercury is the less studied planet in the solar system, in the inner solar system. We only 2 missions having visited the planet, and a 3rd mission going there. With respect to Mars, where we have a 40 mission, and so we have a few frames at high resolution that let us study these gully-like features in detail.
The Martian Dark Army.
Yeah.
So we have a question about the composition, and I would skip it because maybe it's answered by Christian. A question about the impact density. Why the lower impact density on Mercury?
Because it's secondary crust. I mean, the moon far side, the lunar highlands are primary crust. So it means it cooled down, the ocean, the magma ocean cooled down, formed, and stayed there unchanged. So it could record all the impacts during the solar system formation. While on Mercury, we had several events of resurfacing processes. So it could record as well all the impacts around 3.9, 4.0 gigayears ago. But actually, many of them have been covered by the volcanic events. So that's why the lower density of craters.
And is there any evidence of landslide?
Yes, I don't remember by, there are some evidence of landslides, and but they are often caused by the impacts. I mean, if, for example, you have a crater wall, another crater hitting the crater wall nearby, and then it causes a landslide. So we have morphological evidence of landslides along crater walls. We don't have evidence of landslides caused by any other process, for example, tectonic processes, or we don't have any recordings of landslides like we have on Mars. I remember seeing some Mars pictures that record the landslides along crater walls. So unfortunately, we don't have that material on Mercury, but yes, I don't remember where, but there are some landslides along crater walls caused by other impacts.
Thank you. Any more questions? Well, maybe someone is still writing. I have a question. The instruments on board Baby Colombo, which one are you waiting with more excitement?
The one I work for is a Symbiosis instrument, which is a suite of cameras. It has a high resolution channel that will picture Mercury up to 5 meters per pixel. And it can cover up to 6% surface with this resolution, but also 20% of the surface with a slightly lower resolution. And then there is the stereo channel that will cover Mercury globally with stereo images that will create a global stereo DTM. And then there is the spectral channel, the spectrometer, that will cover globally Mercury and will finally tell us the composition of Mercury's crust, which is still a mystery.
And what's the current resolution for the data sets on Mercury?
We have an average resolution of 166 meters per pixel, which is the resolution of the base maps you are looking here in the screen. Of course, there are also frames with higher resolution. We have frames up to 8 meters per pixel resolution, but the highest resolution frames only cover 1 or 2% of the surface, while we can cover a good portion of the surface with 100 meters per pixel resolution or lower. Yeah, there is a wealth of data coming from the messenger mission that can help us studying the morphology and selecting targets for Baby Colombo.